In this section, we explain how to calculate the reaction forces. When the uniformly distributed action force acts on a simply supported beam. A simply supported beam is a statically determinate structure with 3 reaction forces and no intermediate hinges. Therefore, all reaction forces can be determined using the equilibrium conditions in 3 directions. For an object at rest, equilibrium in all directions must be satisfied. The simply supported beam to be discussed has a hinge support at point A, a roller support at point B, and a length of L, as shown in the figure. We will determine the reaction forces when the uniformly distributed action force W acts on a simply supported beam, as shown in the figure. For a beam, a free end allows movement in all directions, vertical, horizontal, and rotational. A roller support allows the beam to move freely, in the horizontal and rotational directions, but restricts movement in the vertical direction. A hinge support allows the beam to rotate freely, but restricts movement in both the vertical and horizontal directions. A fixed support restricts movement of the beam in all directions, vertical, horizontal, and rotational. Steps for determining reaction forces. Step 1. Create a free body diagram of the reaction forces. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. Step 1. Create a free body diagram of the reaction forces. The hinge support at point A restrains both the vertical and horizontal movements of the beam, so the reaction forces at point A are the vertical reaction force VA, which restrains vertical movement, and the horizontal reaction force HA, which restrains horizontal movement. The roller support at point B restrains the vertical movement of the beam, so the reaction force at point B is the vertical reaction force VB, which restrains vertical movement. The directions of the reaction forces are assumed as follows: VA is upward, HA is rightward, and VB is upward, as shown in the figure. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. The distributed action force W is a force per unit length, so its unit is, not Newton, but Newton per meter. Therefore, the distributed action force W cannot be directly summed as a force. As we proceed with summing forces and moments, it is necessary to replace the distributed action force W with an equivalent force. Let's identify the 3 components of the force, due to the distributed action force W in the figure. The distributed action force W acts over a length L, so its magnitude is W multiplied by L. In other words, the magnitude of the force due to the distributed action force W is the area of the rectangle formed by W and L. The direction is downward, and the point of application along the beam's axis, is at the centroid of this rectangle, which is the center of the span, point C. We will now analyze the equilibrium of forces, in the vertical direction. Refer to the free body diagram of the reaction forces, for the vertical forces. The vertical forces are VA at point A, W multiplied by L at point C, and VB at point B. We will derive the equilibrium equation, for these forces. In the vertical force summation, forces acting upward are considered positive. Let's clarify this. The force VA acts upward, so it contributes, plus VA. The force W multiplied by L acts downward, so its contribution is minus W multiplied by L. The force VB acts upward, so it contributes, plus VB. To achieve equilibrium of moments, the algebraic sum must be 0. This concludes the discussion on vertical forces. We will now analyze the equilibrium of forces, in the horizontal direction. Refer to the free body diagram of the reaction forces, for the horizontal forces. The only horizontal force is HA at point A. Since HA is the only horizontal force, the equilibrium equation can be expressed as follows. We will now analyze the rotational equilibrium of moments. First, examine the lines of action for all forces. The lines of action are as follows. The line of action for VA. The line of action for HA. The line of action for W multiplied by L. And the line of action for VB. Next, select the center of rotation. Choosing a point through which as many lines of action of the unknown reaction forces pass as possible, will simplify the calculations for determining these reaction forces. In this case, we will select point B, through which the lines of action of the unknown forces VB and H pass, as the center of rotation. Then, calculate the shortest distance from each line of action to the center of rotation at point B. This shortest distance will serve as the moment arm length for each force relative to the center of rotation. The arm length for the force VA is L. Since the line of action of the force HA passes through point B, the arm length is 0. The arm length for the force W multiplied by L is 1/2 of L. Since the line of action of the force VB also passes through point B, the arm length is 0. We will derive the equilibrium equation for these moments. In the summation of moments, clockwise moments are considered positive. The center of rotation is point B. Let's clarify this. The force VA acts clockwise around the center of rotation, hence it contributes, plus VA, multiplied by L. Since the arm length of HA, with respect to the center of rotation is 0, its contribution is 0. the force W multiplied by L, acts counterclockwise around the center of rotation, so its contribution is, minus W multiplied by L, and multiplied by 1/2 of, L. The arm length of VB, with respect to the center of rotation is also 0, so its contribution is, 0. To achieve equilibrium of moments, the algebraic sum must be, 0. This concludes the discussion on rotational equilibrium. Through the equilibrium of forces in three directions, the reaction forces VA, HA, and VB are determined as follows. The calculated signs are based on the free body diagram, on the left. The positive sign of VA indicates that this reaction force acts upward, which is consistent with the vector assumed in the free body diagram. Since HA is 0, there is no direction associated with it. The positive sign of VB indicates that this reaction force acts upward, which is consistent with the vector assumed in the free body diagram.